Welcome to Lab 5 Magnetic Braking with Faraday's Law. First, the purpose of the lab: to collect data on a magnetic fielding through an aluminum tube in order to observe and apply Faraday's Law. Second, fundamentals: we will be using Faraday's Law, Biot-Savart Law, using second and third law, Ohm's Law, magnetic force on a loop, and the time derivative of magnetic flux of a dipole. The result is the experiment time is 1.456 seconds. The computational time is 1.97 seconds. Next, we have the system and surroundings. The system is the aluminum tube and the magnetic. The surroundings is everything else in the room. The procedures: first, drop the magnetic into the aluminum foil tube, then record the time takes the magnetic to fill. Next, record the length of the tube. Finally, repeat this for 5 times. Then we have some assumptions. First, air resistance acting on the failing magnet is negligible. Second, bar magnet is equal to the magnetic dipole. Last, only force acting on the magnetic are gravity and the magnetic. Now we have some data. The time of the 5 trials are shown on the left chart. The length of the tube is 0.03 meters. The width is 0.006 meters. The inner radius is 0.02 meters. The outer radius is 0.032 meters. The mu is 2.1968. The magnetic dipole is 2.197. The mass of the magnet is 0.025 kilograms. Next, we have the giroscope code. This slide is showing all the values we need to use during the calculation. Now we have more code. The first block of the code is showing the dipole of the bar magnet. The second method is showing the calculation of the derivative of the flux over time. On this part of the code, I determined the motion prediction and the visualization of the magnet as it moved through the tube. We treated the tube as a stack of end rings, and we calculate the magnetic force on the magnet due to each ring. Therefore, the total magnetic force was equal to the sum of the magnetic force acting on the magnet from each ring. We then determined the F-net by summing the gravitational force and the magnetic force, and we used this value to calculate the magnetic velocity and updated the position as we calculate to pass through the loop. Here's the result of my code. Then some result. The experiment time is 1.456 seconds. The computational time is 1.97. The percent difference is about 30%. How might the computational system be made more accurate? First, divide the tube into more rings. Second, repeat more trials. Last, recalculate the magnetic dipole moment to obtain a more accurate value. Then we have the potential source of errors. First, incorrect magnetic dipole moment obtained from experiment 3, which resulted in inaccurate computational model. Second, magnet may not have been dropped straight, causing it to hit the walls of the tube. Last, human errors in recording the time. Last but not least, we have some what-if questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the diameter of the failing magnet change? Large induced could lead to stronger magnetic field, could lead to great opposing magnetic force. Therefore, the magnet will fall slower through the tube. What if holes or slots were cut into the tube? How would this affect the ring current in your model? The hole would affect the induced current, lead to an overall decrease. Overall decreasing current will lead to decreasing magnetic force. Therefore, the magnet will fall faster through the tube. Thank you for watching.